we were at transpose of a matrix. Transpose of a matrix. If you have A as a matrix, then the transpose of this matrix is called A complement. This we had studied. And A complement is formed by interchanging the rows and columns of this, right? And we saw some properties also for transpose of a matrix. The properties were like AB transpose equal to A, B transpose, A transpose. So those are done. So let's go further with this on transpose. Let's do one or two problems and then we will pick up what you call our idea, our next course. Okay, so let's say we have a problem example, and this says A is a matrix which is given by 3 root 3 and 2. We will be basically verifying the properties, and 4 2 0, right? 4 2 0, and you have a matrix B, and B is given as, these are typically 2 mark 3 mark questions. Okay, 2 1 2 and 1 2 4. These are two matrices, and you are asked to verify your law. These are two matrices given, and everything we are going to do is based on these two matrices itself. Okay, so this is your parent matrix, and first thing they're asking us to prove is that prove that a complement of a complement, or A transpose transpose, is equal to A. Will we be able to do this? Right? So shall we find out what is A transpose? So let's go by the left hand side. The left hand side is A transpose transpose. That means, what should we do? We should do transpose of A, which is 3 4 and then root 2 2 and then 2 0, right? And we have to find the transpose of this again. So the transpose of this will be 3 root 2 2 4 2 0, which means you have come back to A and you have verified the. Fine. Okay. Can we do for this one? If they give you a question, they will give you this only, that AB transpose is always equal to B transpose A transpose. The other ones are pretty easy. You studied the other day. A plus B transpose is equal to A transpose plus B transpose. This will be an easy calculation. So usually they don't give this. And another is a scalar multiplied with B transpose equal to A into B transpose. So kindly do this one. Try to verify this. AB, and then you have to make a transpose of it. Shall we? First of all, check whether A and B can be multiplied or not. What is A? A is the, how many rows? 2 rows, 3 columns. And what about this? 2 rows and 3 columns. Will you be able to multiply this? No. So how does this law hold? This law will hold only when you have got square matrices. In this particular example, this will not hold. Okay. So verify that KB. That's why they have not given you in this one. Okay, let's take another question. Let's say, for example, you have A as a matrix which is given by negative 2, 4, 5. Children, tell me, what about this matrix? This is a 3 rows and 1 column. 3 rows and 1 column. So B as a matrix, to be able to be multiplied with this, should be a 1 into something, right? So B is 1, 3, 6. 1, 3, negative 6. Now what is B? B is 1 row, 3 column. Therefore, my AB will be a matrix which will be a 3 cross 3 matrix. Now check for that. Okay, what is my left hand side? My left hand side is AB transpose. So let's do first A into B. So 2 multiplied by 1, negative 2 into 1. So Then, yeah. After you do negative 2 into 1, then do you have any other number? How do you multiply? Rows with the column. So what is the row out here? Negative 2. What is the column out here? 1. So we can't do anything more than that. Then negative 2 will multiply with 3. Negative 2 multiplies with 3. And then negative 2 multiplies with negative 6. After that, 4 multiplies with 1. Then 4 multiplies with 3. And then 4 multiplies with negative 6. Followed by 5 multiplies with 1. Then 5 multiplies with 3 and 5 multiplies with negative 6. So what do we get? And you have to do the complement of this. So let's get the matrix first. So it will be a negative 2, negative 6, 12, 4, 12, negative 24, 5, 15, negative 30. And now you have to do the complement of this, which will be 2, 4, 5, minus 6, 12, 15, and 12, negative 24, negative 30. Check the RHS now. RHS, we are supposed to take the complements first. So if you take RHS is B complement into A complement. So B complement is 1, 3, negative 6, and A complement would be negative 2, 4, 5. Right? And we are supposed to do B complement, A complement. So rows will multiply columns. So 1 into A is negative 2. So 1 multiplies with negative 2, rows multiplies column, then 1 multiplies 4, 1 multiplies 5. This is the row. Then 3 multiplies negative 2, 3 multiplies 4, 3 multiplies 5. Negative 6 multiplies negative 2, negative 6 multiplies 4, negative 6 multiplies 5. So what do we get? We get negative 2, 4, 5, negative 6, 12, 15, 12, negative 24, negative 30. I think that's it. LHS is equal to RHS. I hope I turned on the right class. Ananya is messaging. Fine. Transpose, okay. Now we will get to our new topic, which is known as symmetric and skew symmetric matrix. Symmetric. This is an easy chapter. Just remembering it is all the issue about. Symmetric matrix. If you have a matrix which equals to its transpose, then the matrix is known as a symmetric matrix. Did you understand? A matrix A is called a symmetric matrix, and for symmetric, the criteria has to be that A should be a square matrix. This is obviously understood. Imagine you are not a square matrix. How can you be equal to your transpose? Your number of rows will become columns, columns will become rows. So transpose means, suppose this is square. You transpose it, it should still look like a square. If it was rectangle and you transpose it, it cannot be. This symmetric criteria cannot be there. So a square matrix A is said to be symmetric only if A prime is equal to A. So as an example, we will take the book example. I am writing this matrix. You just write the, what do you call, 2, negative 1.5, and then negative 1, 3. You try to write the transpose. A transpose becomes against root 3, 2, 3, then 2, negative 1.5, negative 1, and 3, negative 1, 1. So we still come to the same. This is called symmetric. The next one that we learn is known as skew symmetric. Skew symmetric matrix. Again, for skew symmetric matrix also you should have a square matrix. You should have a square matrix. The only difference here is that A will be equal to negative of A transpose. A will be equal to negative of A transpose, or A transpose is negative A. Rather, the better way to put it would be that if you have a square matrix A such that the transpose of the matrix is negative of the matrix, then it is called skew symmetric. One is symmetric and one is skew symmetric. Skew symmetric examples are A equal to EF. Try to do is A transpose, you will get 0, negative E, negative F, and then you will get E, 0, negative G, and you will get F, G. So you find that which is equal to nothing but negative of A. So this is a skew symmetric matrix. Understood? So what is the criteria for symmetric or skew symmetric? One, we should have transpose. Then second, there should be square matrix. If you make a transpose and you get the matrix back, then it is symmetric. If you make a transpose and you get the negative of the matrix back, then it is known as skew symmetric. Some theorems based on this, okay? Some theorems and some case which will be based on this. The first theorem, though there is no proof, but you should know about it. The first theorem says that for every square matrix A, for every square matrix A with real numbers, mind you, so you can have natural numbers, integers, whole numbers with real numbers, entries. Look at it. It says A plus complement of A. Now A plus complement of A will also be a matrix, agreed? For every square matrix A with real number entries, A plus this will be a symmetric matrix. Achha, children, what is the meaning of this line? The meaning of this line is that if you take a matrix A plus A dash, if you say B is one of these matrix, then B dash or B complement should be same as again A plus A dash, such that both are same, right? But what is the new thing that you are learning here? The new thing that we are learning is that if I have a square matrix and I add it with its transpose, I get a symmetric matrix. Children, very easy to read but difficult to understand. See, square matrix. I have a square matrix. I add it with its transpose. I get another matrix. This matrix is symmetric. Means if I transpose this matrix, they should be same. Means if you add this, B is a matrix and you get B, B and all. So finally you should get B prime should be equal to B. Then only it's symmetric. Did you understand? And there is another part to it. The other part will say A minus A prime will always be a skew symmetric matrix. So rather you can say the addition of a square matrix with its transpose yields me a symmetric matrix. However, the difference between a matrix, square matrix and its transpose will yield you a skew symmetric matrix. Agreed? So let us see how this is proved. Okay. So the first one we are trying to say A plus A prime will yield me a symmetric matrix. A plus A prime will yield me a symmetric matrix, and A is a square matrix. A is a square matrix, and every element belongs to the set of real numbers R. Fine. So we say after adding these two, we get a matrix B, which is A plus A prime. Yes or no, children? Now, what is the theorem saying? Theorem is saying B is symmetric. That means B should be equal to B complement. Okay. So let's do this. If this is the case, then this can be further. B is this. Now, what is complement of B? I'm straight away taking complement of B. Means end of the day, this should work out and come out as B. Agreed. Either B you prove as B complement or B complement you prove as B. So B complement will become what? A plus A complement whole complement. Agreed? If you have two matrices and you take their complement, you can deal them separately and you can say A plus A complement. Agreed? This is A complement plus A. Now, is matrix multiplication is always commutative. Was this not your B? So you have proved that A plus A complement is a symmetric matrix. Similarly, we will prove the other finding. The other finding was that if A is a square matrix, A minus A complement will always give me a skew symmetric matrix. So let's prove the skew symmetric matrix. Let's say let C be a matrix which is A minus A complement. So C's complement is equal. Now what will you prove? You will prove that C is equal to negative C complement, or we will say C complement is equal to negative C. So C complement is what? A minus A complements whole complement, which is equal to A complement minus A complement whole complement, which is equal to A complement minus A. Now this can be written as, put a negative out here. Can I not write it as A minus A complement? And is this not negative C? Okay? Try to do it on your own. Remember, addition of a square matrix with its transpose gives me a symmetric matrix, whereas the difference of a square matrix and its transpose will always give me a skew symmetric matrix. A symmetric matrix is one in which transpose of the matrix is equal to the matrix. A skew symmetric matrix is one in which transpose of the matrix is negative of the matrix. Now, subtraction is not good. So it's always A minus A complement. So two theorems here. The next theorem is the next theorem. What was the first one? The one that we did right now. The next theorem says every square matrix can be expressed Every square matrix can be expressed as the sum of a symmetric and skew symmetric matrix. Which means if A is any square matrix, you can show this as half of A plus A prime, this is the symmetric part, and half of A minus A prime. In fact, if you add all of this will become A. Just see half of A, and all this side is also half of A. So half of A will give you A, and again half of A prime, half A. So this will cancel out. Every square matrix can be represented as a sum of symmetric matrix and a skew symmetric matrix. Half is just what you call a scalar multiple. Based on this, now we will have our problems. Theorem is fine with you? Okay, now based on this, let's do a problem. Now these will be little bit long problems, but are very easy. Express the matrix B given by 2, -2 and -4, okay, -1, 3 and 4, and 1, -2, -3. Express this matrix as the sum of a symmetric and skew symmetric matrix. Express this as the sum of a symmetric and skew symmetric matrix. When they say sum of a symmetric and skew symmetric matrix, there can always be a scalar multiple in front of it. I hope you know that, right? I also, what I have to show here is that that this particular matrix B can be shown as B is to be shown as a symmetric plus a skew symmetric. Now this also will be a matrix out of which there can be some lambda or something as a what you call scalar multiple. So need not worry on that. So let's do. So let's go by our solution. Our solution would be, let's first find out what is B complement, because we can create a symmetric matrix only by adding B with B complement. So let's have B complement. B complement would be 2, -1, 1, -2, 3, -2, -4, 4, -3. This is B complement. Okay. And then we can have a square matrix. That's how they do. Let P be a square matrix, and this square matrix is represented as half of B plus B prime. Now what is B plus B prime? B plus B prime is a symmetric matrix, but you have to finally show that every matrix can be represented, this matrix can be represented as symmetric plus skew symmetric. Okay, so let's do this, shall we? So this would be a half. Let's go inside. B and B prime you are adding, right? So 2 and 2 will give you 4, -1 and 2 will give you -3, 1 and -3, and this is -3, and this is 6, this is 2, -3, 2, -6. Further, it can be shown now as 4 becomes 2, negative 3 by 2, then negative 3 by 2, then negative 3 by 2, we have 3, then 1, negative 3 by 2, then 1, negative 3. This is ultimately the matrix P. Children, I hope you're with me. I have to show this as a sum of symmetric and skew symmetric. First, I'm trying to form a symmetric matrix. So I got P something like this. Now, is this symmetric or not? How will you get to know? You check P complement. Check P complement. So if I check P complement now, I get 2, negative 3 by 2, negative 3 by 2, negative 3 by 2, 3, 1, negative 3 by 2, 1, negative 3. This is P complement. Now, are you finding that P complement is equal to P? Sorry, is equal to P. So P is a symmetric matrix, right? That is half B plus B prime is symmetric. Half B plus B prime is symmetric. Now we have just proved the symmetric part. Now we have to show now you have to show the skew symmetric part also. Which one? Whether by theorem, but you have to work out is show that express. Okay. Ultimately, we always know that B as a matrix can be represented as half of B plus B prime plus half of B minus B prime. Children, this part is skew symmetric. This part is symmetric. This is what you have to establish. And so far, how much have you done, Zoe? You have just done this much portion. That you have found that this is symmetric. Now you try to find out the skew symmetric part. So what do we write in skew symmetric? Can I make it small now? In skew symmetric, we will say that let there be a matrix Q. Now we will take a matrix Q and we will say Q is equal to half of B minus, we'll take a matrix Q now. We will say let Q equal to half of B minus B prime. So Q is equal to how much? Half B minus B prime. B minus B prime. 2 minus 2 is 0. Minus 2 minus 1 minus 3. Then minus 4 minus 1 minus 5. Then minus 1 minus of minus 2, that is 1. 3 minus 3, 0. Skew symmetric means diagonal you will get 0. And 4 plus 2 will give you 6. And on this side 1 plus 4 will give me 5. And then minus 2 and 4 will give me minus 6. And minus 3 minus of minus is plus 3, which gives me 0. Further this becomes 0, negative 3 by 2, negative 5 by 2, half 0, 3, 5 by 2, negative 3, 0. Right? I try to see what is Q prime. Q prime is 0, half A. But 0 half 3 by 2 होना चाहिए ना? How did you get this one? This one, these two there is some garbar here. Minus 2 minus, or 1 minute, minus 2 minus 1. Minus 2 plus 1 is minus 1. There is a mistake here. This should be minus 1. This should be minus 1. This should be minus 1. This should be 0. Now check. So this would be minus 1 by 2, 0. So 1 by 2, and here I will get a 5 by 2, then transpose it, then I'll get a negative half, 0, and a negative 3. I have a negative 5 by 2, then I have 3, and I have 0. Now this is equal to negative q. Yes? Yes. Therefore, q is what? Skew symmetric. Or half b minus b dash is skew symmetric. Now you do your addition. Now let's add half b plus b prime plus half b minus b prime. So this is half b, right, plus half b. They have not added, they have not done this shortcut, they've added the complete thing. So add p plus q now. Let's add p and q. What was p? P was 2. 2 plus 0 will give me a 2. Then minus 3 by 2 and minus 1 by 2, minus 4 by 2, which is minus 2. Then minus 3 by 2 and minus 5 by 2 is minus 8 by 2, which is minus 4. Then I have minus 3 by 2 and 1, which is a minus 2 by 2, which is minus 1. Then I have a 3 added with a 0, which is a 3. And then I have 1 added with 3, which gives me 4. And after that, I have a negative 3 by 2 and negative 5 by 2, which will give me a negative 2. Negative 4. Which one? This is negative 3 by 2. Yeah, it will be 1 there, sorry. And 5 by 2, negative 3, 5. So this will be 1. Yes, 2 by 2, which will be 1. 1 plus 3 is a negative 2. And negative 3 plus 0 is a negative 3. Is this correct? Okay. So this and this is nothing but equal to b. So you prove that. Fine. Shall we do some exercise problems? Okay, this brings you to the next exercise, which is very easy. Let's do question number 8. I'm writing, you try to, we'll do together. Come, don't worry. I have a matrix, is small, 1, 5, 2 by 2 matrix, 6, 7. Whenever you are playing with symmetric, skew symmetric, okay, you verify that a plus a dash is, verify, just a plus a dash is symmetric. Just verify. So what do you need to do? You first need to calculate a complement, which will be a 1, 6 and 5, 7. Correct? Now you do a plus a prime. A plus a prime gives you what? 1 plus 1, 2. Then 5 plus 6, 11. 6 plus 5, 11. 7 plus 7, 14. And this is some matrix P. Let P be equal to this. Now see what is P complement. P complement is 2, 11, 11, 14. So since P is equal to P complement, therefore A plus A complement is symmetric. So rather we should write, therefore first we should write P is symmetric, that is A plus A prime. Easy? Okay. Can you now show A minus A complement is skew symmetric? Just show A minus A complement is skew symmetric. Once you're done, let me know. You can write let Q equal to A minus A complement. First of all, find out what is A complement. First, find out what is A complement. A complement is already with us. So we say let Q equal to A minus A complement. Let's do that. A minus A complement. So 1 minus 1 gives me a 0. Q symmetric means the diagonal will come 0. Then 5 minus 6 is negative 1. 6 minus 5 is 1. And a 7 minus 7 is 0. Right? Okay. Then do Q complement. Q complement would be a 0, 1, negative 1, 0. Right? Which is equal to a negative of Q. Therefore, we say Q is skew symmetric. That is A minus A complement is skew symmetric. Children, while doing the problem, keep an eye that A was always a square matrix with which we started, right? So the same type of problem that we did, but I would not give you a 2 by 2 matrix. I am giving you a चलो पहले ये कर लेते हैं, then we will do that problem, and then we move to elementary operations, which is the last part of the chapter. So right, A is given as, there's a question, A is given as cos alpha sin alpha, cos alpha sin alpha, negative sin alpha, and out here I have cos alpha, right? This is my matrix, and it says, does this matrix have real entries? We said symmetric and skew symmetric will always be when the entries are real. Are the entries real? Hey, sine of a function is always from 0 to 1 and everything is real. Cos of a function is always, sine of a function minus 1 to 1, cos is also minus 1 to 1. They are real. That's why they say that, right? And further they have given you A plus A complement is equal to an identity matrix. In that case, children, you need to get the value for alpha. So let's do A complement quickly. Let's do A complement. A complement would be cos alpha, sin alpha, then negative sin alpha and cos alpha. And if you add these two, you get an identity matrix. Identity matrix means what? A plus A prime. So let's see what is A plus A prime. If you add these two, you get 2 cos alpha, right? You get a 0 out here, and then again you get a 0 out here, you get 2 cos alpha. But since this is equal to identity matrix, which is equal to 1, 0, 0, 1, you can say 2 cos alpha is equal to 1. So cos alpha is equal to 1 by 2. That means alpha should be equal to cos inverse 1 by 2, which should be a pi by 3, which is 60 degrees. Samjhing? Pretty easy, right? Okay, one more question. Done? I have a matrix A and I have a matrix B, and both these matrices are symmetric. Both these matrices are symmetric, okay? And they are of same order. Okay, now why are they saying they are of same order? Because A and B are two different matrices. A is a symmetric matrix, B is a symmetric matrix, but the order is same. Order is same. They are asking you that AB minus BA, AB minus BA, we have to check this, whether this is a symmetric, skew symmetric, 0 or identity. So how will you do this? Take a very same order symmetric matrix. So let A we have to suppose. What can we suppose? 1, 2, 2, 1. Right? What is the transpose of A? Now the transpose of A is 1, 2, 2, 1. That means this is typically a symmetric matrix. A is a symmetric matrix. Then take B also as a symmetric matrix. B can be made what? 2, 1, 1, 2. This is also a symmetric matrix. Right? Now just do AB. AB. Can we do AB? Row multiplied by column. So 1 into 2 plus 2 into 1. Then 1 into 1 plus 2 into 2. Then 1 into 1 plus 2 into 1. 1 into, sorry, गड़बड़ हो गया. Row 1 into 2 plus 2 into 1. 1 into 2 plus 2 into 1. 1 into 1 and 2 into 2. Okay, pretty fine. Then 2 into column. Two into 2 plus 1 into 1, then 2 into 1 plus 2 into, once you take off your eyes it goes away, 2 into 1 plus 1 into 2. Two ones are 2, 2 ones are 2, 2 plus 2, 4, 1 ones are 1, 2 twos are 4, 5, 2 twos are 4 plus 1, 5, and 2 ones are 2.
So what do you
have to check what is AB minus BA. AB I have done, BA you do. BA. Okay, BA would be what? BA. 2 into 1 is 2 plus 1 into 2 is 2. Then 2 into 2 is 4 plus 1 into 1 is 1. Then 1 into 2 is 2 and 2 into 2 is 4. And then 1 into 2 is 2 plus 2 into 1 is 2. So, 1 into second round, row 1 into 1 is 1, 1, 1 into 1 is 1 plus this. Okay, right, fine. So this gives me what? This gives me 4, 5, 5, 4. Now do AB minus BA. You are actually getting what? Zero matrix. So the options given to you were that it will be a skew symmetric, symmetric, zero, identity. So it's a zero matrix. Are we fine? And then the exercise is all about this only. Sometimes they have given you smaller numbers, sometimes they have given you higher number. One trigonometric question let us do. Okay, let's do one trigonometric question. It's A is equal to cos alpha sin alpha and is given as negative sin alpha and cos alpha. This is my matrix A. You need to get that A complement A is equal to I. A complement A. A complement with A is equal to I. So first of all, find out what is A complement. A complement would be cos alpha minus sin alpha, cos alpha. And now we are supposed to find A complement A. So let's do it. Rows into column. Cos alpha into cos alpha will be cos square alpha. Then minus sin alpha into minus sin alpha will be plus sin square alpha. So this is already coming as 1. You have to prove that it is identity matrix. Here we should get 0. So cos alpha into sin alpha is cos alpha sin alpha minus sin alpha cos alpha. So we're getting a 0 out here. Here again we should get a 0. So it's a negative sin. Now this one, negative sin alpha into cos, sorry, sin alpha into cos alpha. So it will be cos alpha sin alpha and again cos alpha into this. So this makes it cos alpha sin alpha, which gets me a 0 here also. And now this multiplied with this will be sin square alpha plus cos square alpha, which is equal to a 1 and a 0 and a 0 and a 1. Yes, this is equal to an identity matrix. Okay. So try the rest of the exercise. Pretty easy. All is with numbers. Now we learned something called elementary operations. This you'll need more in dividends. I'm saying determinants. When we do, we will be using this a lot. Elementary operations. And elementary operations are actually, there are 6 elementary operations divided as 3 for rows and 3 for columns. I already told you at the start of the class that a matrix does not have an overall value, but a determinant does have a value. So when you carry out these elementary operations, the overall determinant's value does not change when we do it in determinants, right? So let's understand what are the elementary operations. Now we will understand the operations only with respect to say columns, but they are applicable to rows also. The first one is known as interchange of any 2 rows or any 2 columns. Mind you children, columns interchange with columns, rows interchange with rows. You can't change a row and a column. Okay? Any 2 rows and any 2 column. So there are some symbols, like say if you have ith row and if you say have a jth row, means something like a second row and a third row, ith row and a jth row, then we will show it like this. Ri can be interchanged with rj. Where are the bigger matrices gone here? Yeah. Bring this here, shift this up. Are we fine? I will not change the value. The matrix doesn't have a value. This is allowed in matrix. That value question will come when you do determinants. It will not change. You'll see. It will not change. Determinant is ultimately cross multiplication products. So end of the day, they will yield you the same things. Okay. So have you understood the first one? Be very careful on this. Okay. Ith row and jth thing. And similarly, if you are doing it with the ith column and you are interchanging with say the jth column, then in that case we'll say Ci is interchanged with Cj. Ci is interchanged with Cj. Interchange of any 2 rows or any 2 columns. Clear? Not that tough. Next. Next is multiplication of elements of a row or column by a non-zero multiplication elements of any row or any column by a non-zero number. That's basically a scalar multiple. Multiplication of elements of a row or column by a non-zero number. So we say that non-zero number we are assuming as k and we can do as K multiplied by Ri, with the condition that K cannot be equal to 0. K into Ri. Similarly, you can also perform a K into a Ci. Can you understand this? If you bring out a scalar multiple, now let's see some examples along with it. Say I had a matrix 1 to 1. Okay, A is a matrix which is given by 1 to 1, and then I have -1 root 3 1, and I have 5 6 7. Okay, I have 5 6 7. What I'm doing here is that I'm doing R1 interchanging with R2. R1 interchanging with R2. After you do this operation, what should you get? You should get -1 root 3 1, 1 2 1, and 5 6 7. Is this understood? This was my matrix. I performed this particular operation, elementary operation on that. That is interchanging any two rows. Interchanging any two rows. Are we fine? Okay. Similarly, you can interchange any two columns also. If you want, you can do a column interchange also on this. Say B is a matrix which is given by 1 to 1, 1 to 1, and -1 root 3 1. That's just the first two rows. Okay. B is a matrix which is given by this. And now what you're going to do this, you're going to perform this one. Okay. So you now say that let my C2 be C2 divided by, how much is they have taken? That's okay. C2 divided by say -1. C2 divided by -1. My column 2 is equal to column 2 divided by -1. So what will you get here? I will get 1 minus 1, 1 and 1 remain unchanged because I'm performing the operation only on column 2. So column 2 divided by -1 is a -2 and a -3 out. Clear? Third one is where children get little bit confused. Third one. Third one, let me explain you in crude language. You have a row. What did you do so far? You interchange this row. You push it up and brought the upper one down. Now what will you do? You have got 3 rows. The second row you will add the elements of third row after they have been multiplied by some scalar multiple which is not equal to 0. Say my second row is 1 to 1. My third row is 5 6 7. So I'll multiply 5 6 7 first with a 2, which makes it 10 12 14. 10 12 14 will be now added to 1 to 1, and 5 6 7 will remain the way they are. 5 6 7 will remain the way they are. ऐसा कोई नहीं जिस रो को कर रहे हो उस रो का वैल्यू चेंज होगा. तो हिंदी में बोले तो किसी एक रो में किसी दूसरे रो के एलिमेंट्स को थोड़ा सा मल्टीप्लाई करके लाके ऐड करेंगे. Right? So we write the addition to the elements of any row or column, the addition to the elements of any row or column. Acha children, just see, stick to this much. The addition to the rows, elements of any rows or column. Pick any row of your choice. That row will have some elements. With that elements, we are going to do some sort of addition. What addition? the elements of another row after they have been multiplied by some non-zero entity. So we say, but the addition will be very corresponding. The corresponding, this will be the most useful one when you do dividends. You have to get zeros, as many zeros. The elements of any other row or column multiplied by a non-zero number. Non-zero number. So let's check what we are trying to say. Let's check what we have. Let me build up an arbitrary matrix. Let A be a matrix which is given by 1, 2, 3, 3, 1, 2, 4, 2, 1. This is my matrix, right? Okay, Zoe, I'm now performing an operation where I say my R2 means which one, beta? 3, 1, 2. Okay, what is my R2? My R2 is this. This is my R2. To my R2 now gets transformed. How does it get transformed? It will be the original R2 added with 2 times of R3. 2 times of R3. So what does this operation give me? This operation will never change R1 and R3. But this is 3. Add 2 times to 4. How much is it? 8. 8 plus 3 makes it 11. 1 plus 2 times of 2, 4. 4 plus 1 is 5. 2 plus 2 times of 1, which will be 4. 2 plus 2 times of 1. Okay. Can you do this operation for me from the original matrix? Okay. From the original matrix, you say C3 is C1 minus 2 times C2. Oh, sorry. This mistake happened. C3 is C3 minus 2 times of C2. C3, that means every change is going to happen in C3. So C1, C2 remains same. 1, 3, 4, and then 2, 1, 2. Now I say my C3 minus 2 times. So 1 minus 6 will give me a minus 5. 3 minus 4 will give me a minus 1. And 4 minus 2 will give me a 2. Check. Which brings us to the last topic, invertible, which we will do in our next class. How to get inverse of matrix. Clear? Easy. So, before we conclude, what all did you learn today? The first thing you learned was, you learned about what is a symmetric matrix. What is the criteria for a symmetric matrix? If A complement equals to A, then A is a symmetric matrix. All right. Then you learned about skew symmetric. Skew symmetric means if A complement is equal to negative of A. For all this, the matrix has to be a square matrix. Then you learned that any matrix can be expressed as the sum of symmetric and skew symmetric. This is what you learned. And then what did you learn? You also learned that if elementary row transformations, 6 elementary transformation. What was the first one? Interchange of any 2 rows or any 2 columns. What was the second one? The multiplication of the elements of a row or column by a non-zero entity. What was the third one? To the elements of a row or a column, add the corresponding elements or elements of the row or column of any other row or column multiplied by a non-zero entity. This will be very much handy for us when we do inverse of a matrix, which will be our last class, that is on Monday. After that, we will get into determinants. You want to get into determinants better, right? We finish determinants and then we get into continuity and differentiation. Then the only thing is left is vector algebra and 3D that we can do later on also. So we can, well, now once you have got into this, now no looking back. Now you'll be totally into calculus. Right?